Okay, good morning, everybody. I hope you're doing well. I'm going to go and show you a few things that I posted online yesterday for you. So we're going to go to the browser. And so we head out to the browser and let's go to this is Math 262. Now, there's a couple of things we have to say here. Um, I have here your test for final exam study guide. So it's actually functioning as both here. So what I want you guys to do here is, and it's actually longer than your final is going to be. It's actually this is much longer than your final, but it's going to cover these topics that you guys see here, and you see predominantly there's a lot of this latest stuff that we haven't done. So this is like a test four, really a test four study guide, but we can make some of this something that you actually turn in for test points, and it'll be due the day of your final, the morning of your final. So let's be very clear. I put this in Canvas already, and your final exam is on Tuesday, June 2nd. So if we go to the schedule, and here's the thing, yeah, your final exam is on Tuesday, June 2nd. So, we could make this due that day as well, and it has to be right before your final. Okay, you're in your final scheduled from 7 a.m. to 9 a.m. So I'm going to have to make sure that the time is actually modified there so that you turn it in right before your final. Now, again, we turn that in right before the final. That's when it's going to be due, right before the final. If you think you're going to take your final and then turn it in sometime later, I'm not going to accept it. It'll be a 0. So I'm going to say that again. Pay attention to the deadlines of when it's due, because there are people who think things are due whenever they get to it, and that's not going to happen. So make sure you do this and get it in before that date. Okay, at 7 a.m. That's when it's due, the day of your final. And some people know this already, so what they do, they actually turn it in earlier, because they know they have a deadline, and that's kind of the responsible thing to do. So they might turn it in the day prior. So you have that June 1st test 4 date there secured for yourself. And, so that's kind of what we're going to do with this last test. It's a take home. Of course, you use your notes, your book. You don't use each other if you cheat, and I can find out because people make the same mistakes. And if I see the same mistakes on different tests, then you get the 0. So that's how we know that you're cheating. So I want to let you know that there's some parameters here for your test 4 and final exam study guide. So take a look at this stuff, and hopefully this helps you prepare. And that's kind of really, a test 4 situation for us. But anyway, so that's what I put up for you. And what else do I want to say? Yeah, make sure that also on your final exam day, if you go to the schedule again, say, here's my schedule. Final exam day is on Tuesday, June 2nd. So part of the reason I did what I did here with your test 4 is because your final exam is so close to that test 4 date. So that's kind of why I did what I did, because it's like the very next day you got to do your final. It's kind of weird. You do a test 4 and then you do a final, So I kind of combined the two things. If you guys notice, it's like a kind of together. And that's kind of what I kind of came up with as a solution for you, is to combine this so that you guys can, use this time to prepare. So as you can see, yes, it's going to be over some sequence and series and the end there of our polar coordinates. But, I might add a few questions. So just be on the lookout, to make it more balanced in a way that it goes back to a few things. I did delete some questions, if you guys want to know the truth, yesterday when I posted this. So I might add a few more just in case. So be on the lookout, in case I do. And yes, Bella, your test 4 is take home. It is take home. You work by yourself. You work. I posted this online for you guys already, so you could get started. It's pretty lengthy. Some of it's pretty quick, though. Some questions are pretty fast, but not all. But just to kind of give you guys a sort of a heads up and a sort of way to study and review. And some of these questions we might have already done, and they might even been in your homework already. So, yeah, look it over. It's completely take home, Marbella. All right. So it's going to be due right before your final exam, and I'm going to adjust the date and time because I'm looking at the date at the time here, and it'll be due really June 2nd prior to 7 a.m. to your final. And that's what people want to know. Make sure you get that done and turn it in. And like I said, you're going to have people who are going to try. I already know there's always that one or two people who, and this is who I'm talking to, the one or two out of the 40 who like just don't get it, you know. So in other words, make sure you guys upload it in a PDF file format to the website. I'm sorry, to Canvas. It's in the assignment portion. So wherever you downloaded it, that's where you upload it in that assignment portion, and that's due before 7 a.m. Also, what to tell you guys, homework is due. Your last homework is also due at that time. And I send a reminder to people on it because it's the same kind of thing. You know, the idea is when you do homework, it's to prepare you for a test. So the idea to do homework after a test is crazy. It's backwards. And that's one thing that I think colleges and universities are really designed to do, is to help people adapt to move forward, not backwards. So meaning if you say, well, I'm going to turn my homework after I do all this stuff. No, it doesn't work that way. Your homework's designed to prepare you for a test. It's not that you take a chance on a test or a final and then do homework later. That's crazy. So it's due, like I sent this out to you guys, and I'll adjust that date and time as well. It's going to be due at the same time. So I'm going to adjust that in Canvas, so look out for that as well. So if you guys have any questions as to what's going on, now's the time to ask. It's a good time to ask here about this, because I did want to get it out, like I said, a week before all of this stuff was due. So anything, any concerns, any sort of issues, bring that up, and we can talk about that. And homework and this study guide, which is really also test 4 worth 150 points, will be due on June 2nd. Okay, prior to your final, prior to 7 a.m. I might even put like 6:59 a.m. Right? So I'm gonna do that. Make it 6:59 a.m. because that's your final exams at 7 a.m. And this is what I've historically done for all my tests and final, that the work is due before the exam, because that work is designed to help you prepare for the exam. That's how it works. We don't do it backwards. So make sure you get that done the way it's designed. And if you don't, then of course you give people the zeros. And that's that, and the doors close. So also make sure, and it's not really an issue with this class for you guys, make sure you guys know how to scan, right? Because you got to use your phone and you got to scan the stuff and you upload it, right? And it's going to be uploaded to the same place as PDF files. Don't take images and try to upload images, because if you do that, it won't accept it. Because I actually put on that thing to accept only PDF. Now, the reason I do that is so that I can grade it and get it back to you. See, there's a feature in Canvas called Speed Grader. And then I could write on that and get it back to you, and it's actually entered in your, whatever, the grade book, I guess, and you guys have access to that in Canvas. So it's all portable in that way. So that's why you have to do it in that kind of way. It doesn't grade like some people put zip files. It doesn't grade that. And it's interesting that people do zip. That represents some knowledge of computers, and I think that's great. But Canvas just doesn't accept zip and doesn't accept images, only PDF, so that we can use SpeedGrader. So okay, and so that's what's going on. And of course, I'll talk a little bit about this, every day. And if you have any other questions, I have office hours and I have email. But okay. So let's go to some of the things that you might see, or I guess not might, you will see, things that are Maclaurin Series. So we have some Maclaurin Series here to talk about. and Maclaurin and Taylor series. And so yesterday we worked with power series, functions that can be described as power series. And we were very limited with those kind of functions, extremely limited. So we want to actually generalize that a bit, and this is where Taylor series and Maclaurin series actually come in. So the idea is simply, it's very simple. It looks like this. If a function can be represented as a power series, right? So we say f of x, when we write this function, we have Cn x minus a to the n. This is the definition of a power series. That will give you C naught x minus a to the 0 plus C1 x minus a to the first power plus C2 x minus a to the second power, and then this goes on forever. So here's the expansion. If I clean this up and I say that's really C naught plus C1 x minus a plus C2 x minus a squared, and I'm going to add another term, x minus a cubed. What we see here is a way to expand a function in terms of a power series if it can be done this way, because not every function can be expanded as power series, only some functions. And so here's kind of just the definition of a power series. And so the question people have here is, how can we describe our coefficients? Cn for all n. So here's where you start, and here's what they're, looking at and say, okay, how can we describe our coefficients for all n? And so what we do here is we start by doing the following. If we let a here, replace a with x, or we can say let x be a. We get a power series expansion, or we should say we get a hint. That means f of a. Remember, we're going to put in here an a everywhere, a. And what that means now is that this term is 0. In fact, all these terms are 0, except the first term. So we get f of a is C naught. Okay, good. Or you can say that C naught is really f of a. So I think maybe we want to look at it that way instead, but it doesn't matter. So here's where we actually see how to describe that first constant, C naught. It's really f of a. Now, we've seen yesterday that we can differentiate. So what I'm going to do here now is I'm going to differentiate this function. And let's go back. Let's get rid of this if we can. That's weird. Okay. So we're going to differentiate f. When we do, and I'm going to get more space here, f prime x, if I differentiate, will now be, I don't know if I want to, I'm just going to do this once for you guys so you can see the details, right? So you guys know about properties of derivatives. And we're going to, properties of derivatives, of course, you have, derivative of sum is sum of derivatives. Anyway, let's just do it once for you guys. And I'm going to pull out the constant. Goes on forever. So we get 0 here. we get 1, we get 2, x minus a. So that f prime x can be described simply as c1 plus 2c2 x minus a, and then you're going to get 3c3 x minus a squared for the next derivative, because it's a third power, and that goes on forever. So we're going to do the same thing we did before now. We're going to say let x be the value a. So wherever there's an x, we're going to plug in a here. So you say here's an a, here's an a, and here's an a, and we end up getting f prime a going to be c1. Right? Or we can say c1 is simply f prime a. Okay, so that's kind of interesting as well. So we're getting an idea here of what our constants look like. We're going to do this again now. So if I say to you, we're now going to take the second derivative. What you see here is, again, d dx now of c1 plus 2c2 x minus a plus 3c3 x minus a squared, and so on. And this will give us, by properties of derivatives, 2c2 plus 6c3 x minus a. Now, you don't have the next term. But it's going to be 12c4 x minus a squared, and then that goes on forever as well. So we're going to let x be a again. So if we replace an a here, wherever there's an x, we're going to see terms go away. This becomes 0 here. This is 0. And you have now f double prime a equals 2c2. Or we can say c2 is f double prime a. And so we are generating the constants here. So we know we got C0, we got C1, and we get C2 here. So we got these constants. We're going to do this again. You say, okay. So as you can see, when I differentiate, I'm getting every constant just by differentiating. So I just have to be clear about what's left here. So we got 6c3 x minus a plus 12c4 x minus a squared. And of course, this goes on forever. And again, by properties of derivatives, we're going to get 6c3 plus 24 x minus a, and you get the rest of the terms. But I didn't write them down. So again, we let x be a here. So here's an a, wherever there's an x. And, maybe I'll write down the next term. I think we need a constant here. Yeah, we have a constant, by the way. I'm going to write down the next term, but I'm going to put a constant. Let's remind that constant here, C4 is still there. And so you have an x minus a when you differentiate, plus this is going to be 60 C5 x minus a squared, and so on. All right, so when you replace this x here with an a, you end up getting f triple prime of a is going to be 6c3, and this portion here is 0 and 0. Or we can say 6c3 is that third derivative evaluated at a. And so what has been observed, and we have to really be double careful. We got to be careful here. There's a 2c2 here, ladies and gentlemen. This one's c1. So let's go back with this one. This means that c2 here is described as f double prime a divided by 2. So we have this term, and this means simply that c3 now is the third derivative over 6. There we go. So we're getting these terms. So we got C2, C3, C1, and to let you guys know, if you continue the process, you should probably consider what's happening with these particular constants here. I'm going to put them in red. You're going to see this constant, 2, over here, 6. The constant here in front is 1, so you know. So we're going to look in particular at these constants. Now, if you went to the fourth derivative, evaluate a, you're going to get 24. C4. And then we say again, or 24C4 is the fourth derivative evaluated at a. What that really means is that C4 will be this number over 24. So again, if we pay attention to the constants here, and we just place it in the bottom. So that particular type of sequence here is actually n factorial. So I want you to note that n factorial is n times n minus 1, n minus 2, all the way down to 2 times 1. So this here is really 4 factorial, which is 4 times 3 times 2 times 1, which is 24. This is 3 factorial, which is 3 times 2 times 1, which is 6. This is 2 factorial, which is 2 times 1. And then up here, this over 1, and we can write it that way. We can remove that and say this is over 1. Well, that's actually 1 factorial. And I want to point out to you, C naught, this is also over 1. And we actually define 0 factorial as 1, so you guys know. So in every case here, the pattern that you guys see, here's what the CNs will be. Cn is going to be Fn evaluated at a over n factorial. And this is good for all n, meaning n equals 0, 1, 2, 3, and so on. So we have a very famous statement in your book, and that's the theorem. If F has a power series expansion, at A, and you might say, well, what does that mean? Well, it just means that we're describing it this way. F of x is a summation n from 0 to infinity, Cn x minus a to the n. And don't forget our interval of convergence. So if we have a power series expansion, then the coefficients Cn are described as the nth derivative evaluated at a over n factorial. So in short, you might say, can we simply replace this? And the answer is yes. And here's what I mean by replace. Can we replace what you see here as constants with this Cn? And the answer is yes. And so you have nth derivative of a over n factorial, x minus a to the n, where n goes to 0 to infinity. And of course, we have this interval of convergence still, described this way. Now, what you're looking at here, and if you really look at the details and you said, let me plug in the values n is 0 and so on. What this means is you really have f of 0 plus well, not 0. I'm jumping ahead. F of a plus f prime a, x minus a, f double prime a over 2 factorial, x minus a squared, and we can continue forever. What you're looking at here, this is known as a Taylor series expansion. And let me give you some more terms. So that first term, when we expand, you can say is f of 0 plus f prime a. I'm still jumping ahead. You can put 1 factorial, x minus a to the 1, plus f double prime a over 2 factorial, x minus a squared. And it looks like, did I even get, maybe I only got another term in. Right, a little bit smaller. F triple prime a over 3 factorial, x minus a cubed. This goes forever. You have a Taylor series expansion. This is called the Taylor series, and this is about a. Now, I want to give you a definition, and this is what we'll be working with today. Maclaurin Series, and it's called Maclaurin Series, after the Irish mathematician Maclaurin. Here, it's very simple. We're going to let a be 0. So this is a power series expansion about 0. So as I was jumping the gun here with the Taylor series and saying, hey, let me put here a, or let me put here 0, I'm now going to replace this wherever there's an a. We replace this with a 0. So you're here, here's a, it's now 0, that's 0. So here's the Maclaurin series expansion. F of x is the sum, n is 0 to infinity, f of n at 0 over n factorial, x to the n. And if you take a closer look at the terms, that's f of 0 plus f prime of 0, x, plus f double prime of 0 over 2 factorial, x squared, f triple prime 0, 3 factorial, x cubed, and that goes on forever. And again, the interval of convergence, I should say, yes, that's the absolute value of x is less than r here. And we don't have to put that in a box, but this is what this is good for. And again, this is the Maclaurin series expansion, and that's what I wanted to get to. It's just simply take the Taylor series and let A be 0. So this is really a power series about 0, and you have all your coefficients here. So the idea is that the coefficient terms that we're looking at, Cn in this case is f of n here, that's the derivative, evaluated at 0 over n factorial for n being 0, 1, 2, 3, and so on. Now, the first example that they always show you for Maclaurin series is they're going to want you to expand or determine the Maclaurin series for this different function, right? Because yesterday our functions were very specially chosen. They were based on the geometric series. So here we have a general function. We're going to take the exponential function. This is always your first, function that they use Maclaurin series on. And they're going to want to expand as a power series. About 0. They can say 0 or really A is 0. Sometimes they put X is 0. So we'll say about A is 0 here for us. So it's a Maclaurin series expansion. And how this starts really is you're determining coefficients. You're just using this formula. So that we know C naught is really f of 0 over 0 factorial, which is e to the 0 over 0 factorial. 1, 1. So my first coefficient is 1. C1 will be f prime of 0 over 1 factorial, and that's the derivative of e to the x evaluated at x equals 0 over 1 factorial, e to the x, which is e to the 0, which is 1. 1 factorial is 1, so that my next coefficient is also 1. So I have C naught being 1, I got C1 being 1, and we're going to see what happens with the rest of the terms. C2, f double prime evaluated at 0 over 2 factorial would be, if I differentiate f prime of x evaluated at x is 0 over 2 factorial. And what you're going to see here is that this is e to the x again. And if we evaluate that as x is 0, that's e to the 0, which is 1. And then 2 factorial is 2. So this constant is 1/2 now. So you got C2 being 1/2. Now similarly, C3, by definition, is that third derivative evaluated at 0 over now 3 factorial, which is the derivative of the second derivative of this function, evaluated at x is 0 over 3 factorial. And you know, since the exponential function, if I keep differentiating that all day long, it's the same function. So this is e to the 0, which is 1. And then 3 factorial is actually 6 because it's 3 times 2 times 1. So this third constant is actually 1/6. So we're looking at these coefficients, and if I did one more, C4, yes, that's the fourth derivative evaluated at 0 over 4 factorial. Similarly, that numerator will be 1, and then we're going to get here 1 over 4 factorial. And so as you can start to see, we start to see a pattern here of our coefficients. And we can go back and say, hey, remember that this is actually, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So we can derive the statement that our constants in this case are going to be 1 over n factorial for all n. N is 0, 1, 2, 3, and 4, because that's what we were seeing here with this particular series. And we're getting, again, these funny shapes. So here's my coefficient for this particular function. Now, what that means for us is that e to the x, ladies and gentlemen, is described as n is 0 to infinity, 1 over n factorial x to the n. So here's the power series expansion for e to the x, and this is about 0. Let's write this down. You can also see this as x to the n over n factorial. N is 0 to infinity. And maybe we should write it that way as well. Okay, now you might say, what about the interval of convergence? Well, what you're going to use here is the ratio test. So we're going to put that there. Interval of convergence here. Well, you use a ratio test. So by the ratio test, let's see what this looks like. An plus 1 over an. Remember, an here will be x to the n over n factorial. So we're going to have an plus 1, x to the n plus 1 over n plus 1 factorial. We get x to the n plus 1 over n plus 1 factorial times n factorial over x to the n in absolute value. Properties here of exponents and definition of factorial. So x to the n times x, n plus 1, n factorial. The factorials are gone. X to the n is gone. Let's see what's left. X is left, and n plus, not that part, n plus 1 is left, it looks like. So we get the absolute value of x over n plus 1, which is the absolute value of x, over the absolute value of n plus 1, which is the absolute value of x over n plus 1. Now, the limit here by the ratio test is the limit of the absolute value of x over n plus 1, and I can pull out my absolute value and get the limit of n plus 1. Now, remember what we say here. We know we have convergence. We assume the absolute value of x is not 0, because if it was 0, that limit's going to be smaller than 1, and it's a trivial solution for convergence only when x is 0, and it makes it trivial because you're adding a bunch of zeros forever, right? We go plug in here the 0. We go, oh, we're adding zeros forever. Of course, it's finite. But if we assume x is not 0, what we know is that as n gets big, 1 over n plus 1 goes to 0. Or, really, the limit of the absolute value of n plus 1 over an, or an plus 1, which is the absolute value of x, limit of 1 over n plus 1, this goes to 0, and that's smaller than 1, really, for all x. Let's say for all x. Because we assume that this is not 0. Absolute value of x is not 0, which means x is not 0. So this is convergence for positive values of x, negative values of x, and we know we have convergence at 0 since that was a trivial solution. And by the ratio test, we know this is the interval of convergence, ladies and gentlemen, is really all real numbers. So we go back to this power series representation, and we say, here's your interval of convergence. It's for all x. And, of course, your book's going to say, okay, and guess what that means? Since we know that e to the x is going to be written as, we start n is 0 to infinity, x to the n over n factorial. If we allow x to be 0 here, or I'm sorry, not 0, that's trivial. We're going to let x be 1. So wherever there's an x, we're going to replace that with a 1. Here's an x, here's an x. So we put a 1 here, we put a 1, and sure enough, you're going to get e to be the sum n is 0 to infinity of 1 over n factorial. So we can actually use a power series to actually determine the exact value of e. Okay, and we can even approximate e to different place values. I might even say something like, oh, if you let n be 4, this is an approximation to e. 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial. Maybe go out to 3 because we're running out of space. That e is approximately, this is 1, 1, 1/2, 1/6. E is approximately the sum of these numbers. And you could go out to 4, 5, whatever, 10. We can approximate e. And if we only went this far, we should say that's 2, plus 1/2 plus 1/6. And, we could get kind of a, multiply this by 3, and keep that alone. And so what is this approximately? We can say this is 2 plus 7/6. Or e is approximately 2 and 7/6. And if that is that case, no, 3, 4/6. And 4/6 is actually 2/3. So e is approximately 2 and 2/3. And that's it's a rough approximation, but if you go to include more terms, you're going to get a better approximation. So anyway, this is a definition of e now. And you could do this all day long. You can find e squared, you can find e to the 1/2, and so on. You can actually approximate e very nicely, and you could use this in a computer program. So here's kind of one way to look at this. And then how to use this to let you guys know. They're going to say to you, write the power series expansion for, they can give you another question. How about e to the minus x? And what you're going to use, again, is the fact that e to the triangle is the sum of triangle to the nth power over n factorial, where n is 0 to infinity. And all you have to plug in now in that triangle is minus x. So you're going to replace that triangle with a minus x. And you get e to the minus x becomes sum n is 0 to infinity minus x to the n over that n factorial, and just use a little algebra, meaning negative 1 to the n, x to the n. So if it's a minus x now, negative 1 to the n, x to the n over n factorial. Here is your power series representation. For e to the minus x. And again, this is good for all x. So here's the power series. It's an alternating series. And then they can say to you, okay, what if they give you, they want to expand or find the power series for something like this, x squared e to the minus x. And in that case, all you do, again, is write the power series expansion for e to the minus x, which you just found. And just use some algebra, because this is x squared times this, distribute, use the distributive property. This is a sum. Remember, you multiply x squared with every term. So that's really going inside the summation symbol. But put that next to the x to the n term. Because you're going to use some properties of exponents again, algebra. So I have my summation here, n is 0 to infinity, negative 1 to the n, x to the n plus 2 over that n factorial. And here's the power series expansion that they're looking for. And that's for x squared, maybe, e to the minus x. Let me go back. Okay, power series expansion for this function here. But if you're looking back at the book, as we've been seeing for some of these expansions, you might say, Mr. Judge, can I let I be n plus 2? You can. And then that means, by the way, n will be I minus 2. And even though they said start this series with n is 0 now, well, if you put 0 for n, that means I is 2. So we're going to start the series here for I being 2 to infinity. And the n power right here becomes I minus 2. And x here, n plus 2, we let that be I. And then down here, instead of an n factorial, you're going to have I minus 2 factorial, because that's what n is. And so, ladies and gentlemen, you say, can I change my letter from I back to n? The answer is yes. So now you can change I to n, and you can see series that look like this. Representing that x squared e to the minus x. Anyway. Okay. Well, that's how we find the power series expansion for, some of those functions. And then, your book does have a demonstration. If they give you the function here of sine, we know we just simply need to start taking derivatives and evaluating at 0. So f prime x, the derivative of sine is cosine. Second derivative of cosine is minus sine. Third derivative of minus sine. So derivative of sine is cosine, that's minus cosine. Fourth derivative, a derivative of cosine, that's going to be sine again. Well, derivative of cosine is minus sine, so it's minus the minus. And let's double check. Start with the function, first derivative, second derivative, third derivative, fourth derivative. Okay. So you're starting back all over again. Now, if we want the Maclaurin series expansion, we're going to have to replace this x here with 0. So wherever there's an x, replace that with 0 here. And we get 0, 0 everywhere. And let's see what this gives us. F of 0 is sine 0, which is 0. F prime of 0 is cosine 0, which is 1. F double prime 0 minus sine 0 will give you 0. F triple prime 0 is minus cosine of 0, which is negative 1. The fourth derivative of 0, sine of 0, which is 0. So notice the pattern here. When you have 1 and 3, you alternate between 1 and negative 1. That's an important detail. But what's also important is 2, you get 0. 4, you get 0. And in fact, the value of the function, it starts with a 0. So I want to point out to you in red, those are thought of as sort of even indice values. And when you have a value, right? So if it's, here's what I'm saying to you. F of an even value at 0 is 0, but f of an odd at 0. And I guess we should spell it out because people might mistake this. So here's the observation. F of even at 0 is going to give you 0. However, f of odd at 0 alternates between plus or minus 1. And how you represent an odd index value is this portion. You can say 2n plus 1 or even 2n minus 1. So for the power series expansion here for sine, if you said, okay, doesn't sine look like this? F of 0 plus f prime of 0. Yes, it's over 1 factorial x plus the double derivative x squared 2 factorial plus the triple derivative at 0, 3 factorial x cubed. The fourth derivative at 0, 4 factorial x to the fourth. If I just look at one of these cycles, we know we get here 0. This portion's 1, 0. This is negative 1. This portion's 0. You end up with really x minus 1 over 3 factorial x cubed, and then this pattern continues forever. So in other words, odd powers. 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh, and that continues forever. And this is how we describe the power series expansion for sine. And we can very easily say here, well, we got factorial. We can say x to the 2n plus 1 over 2n plus 1 factorial. And I guess we have to start that when n equals 0. And we forgot something, the alternating mechanism. Because this alternates, plus, minus, plus, minus. So ladies and gentlemen, here's your power series expansion for sine. And I just want to say, by the ratio test, you're also going to find that this works for all real numbers. We might have actually looked at that in the past. That interval of convergence is all real numbers. And we seen yesterday that if I use some calculus and I differentiate a power series, x minus 1 over, I guess I could do the following. Yeah, let's do this one. 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th, and that goes on forever. Okay, we're going to differentiate this. So that's going to be 1 minus 3x squared over 3 factorial plus 5 over 5 factorial x to the 4th minus 1 over 7 factorial, and there's a 7 there. We're going to differentiate. And that's x to the 6th power, and that pattern continues forever. And don't forget, the derivative of sine is cosine. So I'm describing cosine now as 1 minus, and doing some algebra. This is 3 over 3 times 2 factorial, x squared, plus 5 over, we're going to deal with the definition here of these factorials, right? So this is going to be 5 times 4 factorial x to the 4th minus 7 over 7 times 6 factorial x to the 6th, and so on, where you have the cancellation again of these constant terms here. And so you end up now with 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and that will alternate and continue forever. Now remember what you're looking at here. 2 and 2 factorial, 4, 4 factorial, 6. These are even numbers. The powers are even, the factorials are even. We represent even by 2n. So when we write this here, we can say x to the 2n here over 2n factorial, and we can start again where n is 0 to infinity. And here's our cosine power series representation. And the interval of convergence, again, is from negative infinity to positive infinity. It is all real numbers. So now you have the power series representation for cosine, ladies and gentlemen. Pretty good. So if we put this all together and just say recall or note, you know, we have ways here. I guess with this last example, I can say to you, what if they said, what's the power series expansion for cosine of maybe x to the 3rd power? Right? What you're going to do is you're going to use what we just talked about, meaning since we can describe cosine of any argument to be the sum where n is 0 to infinity, that argument to the 2n power over 2n factorial. Oh, thank you, Kirby. Yes, we do. Because this is, again, what? Alternating. Thank you. We forgot to put that. So we need to put the alternating mechanism. And negative 1 to the n, x to the 2n. Okay. Okay, good job. So here's the mechanism you use. You just replace now here this triangle with really x to the third power. So we get these power series expansions, and we'll change that to blue so that cosine x to the third power is the summation n is 0 to infinity x to the third power raised to the 2n over 2n factorial, and don't forget that negative 1 to the n. And it's really x to the 6n now with negative 1 to the n over that 2n. And we'll put that in parentheses factorial. Okay, so let's put this in parentheses because as you're reading it, it's kind of incorrect. You need to put that 2n. Okay. And that's how you handle cosine x to the third. And then you might say another example. What if they want a power series expansion for sine of pi x? Well, you have to use the representation for sine, right? So sum n is 0 to infinity, negative 1 to the n, x to the 2m plus 1 over 2m plus 1 factorial. And yeah, I'm going to write it this way here. So we're going to say this is going to be the sine of, change this to a triangle if you guys like that. So we just have to fill in the argument with pi x. So plug in a pi x here and a pi x and just use some algebra. So that sine pi x is the sum n is 0 to infinity, negative 1 to the n, pi x to the 2m plus 1, everything over 2m plus 1 factorial. So here's where you use the algebra with the powers here. This is going to be replaced with pi 2m plus 1 x 2m plus 1, this portion right here. So your final answer is going to be sine pi x becomes the sum n is 0 to infinity, negative 1 to the n, pi to the 2m plus 1, x to the 2m plus 1, everything over 2m plus 1 factorial. And again, this is good for all real numbers, because the idea was that you did the ratio test for sine and you seen that limit for all x to be less than 0 by the ratio test, and then if you took the derivative for cosine, it applies to that cosine function as well. Anyway, so here's how we use Maclaurin series expansions today. So I'm going to look at a couple of these things, maybe say to you guys for homework. You're going to amend the homework. You got 12, 10, some expansions here that are going to help you again for your final. We're going to look at, for today, well, we can look at like 23 to 28 all. We'll continue with some of these. And then I'm going to actually give you 39 to 42. We'll see some of those. That's applications of it. And really 47 to 50. We'll see some of those. And we might see tomorrow, we will see tomorrow, 51 to like 54 all. And don't forget from 3 to 10 as well. So these are Maclaurin, and then we'll look at Taylor Series as well, a couple of Taylor Series expansions, but it's mainly Maclaurin Series for this section. So, I mean, get started on some of these here, some of these questions. And if you like, you say, oh, no, you know, let's make them odd here. All right, let's not make them all. I apologize. I know you have that test 4 to work with. So do the odds. But this will help you even do test 4, since I think I took some of them, you know, from that place as well. Anyway, okay, so we're out of time. So, ladies and gentlemen, if there's any questions or issues, you know, please contact me for, you know, during office hours. And if not, of course, email. And make sure, again, I'm going to modify some of those deadlines for you guys right before your final exam, your homework's due, and this test 4/study guide is due. It's take home. You work by yourself. Okay, you can't work with people on it. We can always catch you cheating, and we can tell by the same exact errors. Very easy to catch people, and they get caught all the time. So anyway, make sure you guys do that, and stay safe. I hope you guys are okay, and we'll see you tomorrow. We'll continue tomorrow with some of these, and okay, have a good day.